What's going on, Alex Bros? In this video, we're going to discuss x-axis symmetry, which is a special kind of symmetry that some graphs have. And symmetry in the sense that, if you were to look at a butterfly, one wing is kind of the mirror image of the other, and the body of the butterfly sort of serves as like a line of symmetry. So if you were to, fold the wings, across over top of the body of the butterfly, you should have one wing matching up exactly with the other. All right, I'm not sure how easy that is in real life, but I think you get what I'm saying. So here we have a graph that is displaying x-axis symmetry, and how we would know that is by examining the two sides that are across from each other relative to the x-axis. If we were to maybe cut this picture out and fold it along the x-axis, then what should happen is that the part that's above the x-axis should overlap with the part that's below it. So that's one way of explaining x-axis symmetry geometrically. We can do this a little more analytically though by examining a special relationship between one of the coordinates of the points that are on one side of the x-axis with their corresponding point on the other side of the x-axis. For instance, if we look at the points 1, 1 and 1, negative 1, these 2 points correspond from each other. They're directly across from each other relative to the x-axis. And you'll notice that the x-coordinate of each point is 1. The y-coordinates are opposite of each other. Okay, so here we have the x-coordinates staying the same, whereas the y-coordinates are opposite of each other. If we look at the next pair of corresponding points, we've got 4, 2 and 4, negative 2. And the same deal there. The x-coordinates between the 2 points are staying the same, whereas the y-coordinates are turning opposites. Last but not least, another pair of corresponding points would be 9, 3 and 9, negative 3. And same observation there that you're probably making, that the x-coordinates are the same, whereas the y-coordinates are opposites of each other. So we can form this into a criterion for a graph. Should it have x-axis symmetry, then it will meet this criterion. Otherwise, if it doesn't meet this criterion, then we won't expect the graph to have x-axis symmetry. So a graph is symmetric with respect to the x-axis if for every point x, y that's on the graph, x, comma, negative y will also be on the same graph. So another way to state this is that, given the y-coordinate of any point that's on the graph that has x-axis symmetry, there's going to be a point on the graph that corresponds to it, in which case its y-coordinate is the opposite of the original. Alright, and that's x-axis symmetry. Another type of symmetry a graph can have is y-axis symmetry. And this is very much the same sort of concept as x-axis symmetry, except the line of symmetry this time is the y-axis. And the same deal as before. This time we're going to look at a graph having y-axis symmetry, and if we imagine cutting this diagram out and folding it along the y-axis, the part that's to the left of the y-axis would overlap with the part that's to the right of it. Okay, in other words, they're mirror images of each other. And this graph has some corresponding points indicated for us. I'll start at the bottom. The first pair of corresponding points is negative 1, negative 3, and positive 1, negative 3. And what you should notice about these 2 points is that the x-coordinates are opposite, whereas the y-coordinates are the same. another pair of corresponding points, negative 2, 0, and positive 2, 0. Same deal as with the last set of corresponding points. The x coordinates are opposite of each other, whereas the y coordinates are the exact same value. And you probably see this coming a mile away. Our last pair of corresponding points that are indicated on this diagram are negative 3, 5 and positive 3, 5. And you'll notice that the x coordinates are opposite, whereas the y coordinates are the same. Hence, a criterion that must be met in order for a graph to have y-axis symmetry. A graph will be symmetric with respect to the y-axis if for every point on this graph, xy, negative x, comma y, is also on the graph. So in other words, if you're given an ordered pair, we can quickly construct the corresponding point, assuming this type of symmetry, by taking the original x coordinate and turning it into its opposite. The very last type of symmetry for now is known as origin symmetry. And this one is it's kind of a combination of both the x and y-axis symmetry, but it's a little more difficult to spot out what the corresponding points are, so that's why I'm here. We have a part of the graph that's in quadrant 1 and also another part that's in quadrant 3, and the graph would have an x-intercept at the origin. And a couple of ways of explaining the symmetry. The first is more of a visual way. If we were to take the part that's in quadrant 1 and do a couple of mirroring effects, the first of those would be to mirror this piece across the y-axis. We'd end up with a piece looking somewhat similar to that. And then the second and final mirroring effect that we would do is with the piece that's in quadrant 2 that we just drew out, reflecting it across the x-axis. And should this graph have origin symmetry, upon doing the two mirroring moves, it should line up with the part that's in quadrant 3. Now you don't have to start with the part that's in quadrant 1. You could also, or you could instead start with the part that's in quadrant 3. And if you were to mirror that across the y-axis, it would end up here. And then if you mirror that piece across the x-axis next, it would line up with the piece that's in quadrant 1. So that's one way of illustrating origin symmetry. Another way is to do it analytically by using corresponding points. Let's start with the point 1, 1. Its corresponding point on this graph is going to be negative 1, negative 1. And you can see what's happening between the values of the ordered pair. Not only are the x values opposite of each other, but so are the y values. The other set of corresponding points would be 2, 8 and negative 2, negative 8. And same deal there. Not only are the x coordinates opposite of each other, but so are the y coordinates. Now here's the reason why I think it's called origin symmetry. If we take any pair of corresponding points, such as these two, we could also consider 2, 8 and negative 2, negative 8, and if we connect those corresponding points, say like a line segment, which I have here, just it's dashed, regardless of which pair of corresponding points you decide to connect, of course they have to be corresponding points, you'll always pass to the origin, which is the ordered pair 0, 0. And so that to me is, it might not be why it's called origin symmetry, exactly, but to me it would make sense. So here's the criterion in order for a graph to have origin symmetry. The graph is symmetric with respect to the origin if for every point x comma y on the graph there's a corresponding point which we can form formulaically where the x coordinate is the opposite of x and the y coordinate is the opposite of y. And so you can form a corresponding point under the assumption it has origin symmetry by taking your provided point x comma y, changing x to its opposite, and also changing y to its opposite. And both need to be changed in order to come up with a corresponding point with a graph that's symmetric with respect to the origin. And that's all I have for you in this video. Alright, thanks for grinding your way through it. If you have any questions, feel free to reach out. Otherwise, I appreciate you watching it, and I'll catch you guys in the next one. Have a good one.